All right, guys. First of all, it looks like the who's who of storage in this room right now. That's kind of cool. So, quick introduction. I'm Steve Wells, and I work for Micron Technology and the Solutions Architecture team. I've been designing SSDs, sometimes said longer than some of the people in this room have been alive. I first started in 1991. And I've been involved in it pretty much since then. My co-presenter is Suresh Ragapal, and he'll be coming in and jumping in with some of the detail in a bit here. I want to start with a question. 25 watts, where did that come from? Anybody know any of the history of 25 watts? And how it ended up landing in the EDSF form factor? Trent obviously discussed 25 watts when he did his presentation. I've been asking around. I'm not exactly sure the answer myself. I have some theories that I've heard. Anybody have any? Is a legacy number from HDD days? An HDD day number? HDD is really 25 watts? I used to work on laptop HDDs, and they were like 3 watts, so obviously they were bigger. So you guys can tell me if you've heard different. At one point in time, when Bill Lynn was around, I asked him, where did this 25 watts come from? And he said, in 8639 connector days, they needed to decide what the specification was for the pin current. And they were like, what should we use, what should we use? And they went, well, the chem card had 25 watts. And so they just decided to use the 25 watts 8639 to help specify the electron flow in the connector. If you get too much electron flow in a pin connector, you start getting electromigration and other problems, and it becomes a reliability concern. The connector guys need to go worry about all of that. And then somehow that seemed to have propagated into the EDSFF informative annex that also called it 25 watts, and I'll talk about that a little bit later. At least an interesting point from my perspective, that was really worrying about current flow, not thermals. And I'm curious if anyone has any better background on that, but it kind of poses the introduction to the question to this statement, which is when we look at Gen6x4, there's a lot of form factors that are claiming 25 watts. Now what do we do? So that's the purpose of this conversation, and there are several things that I'm going to be pointing out to this thing. I am not advocating in any way, shape, or form that we need to abandon 25-watt form factors. At the same time, we see that we believe there's going to be some work that might be required within this. So I think a lot of people would say, oh, well, if I have a 25-watt or a 20-watt Gen 4 drive, then it's going to be double that for Gen 5 and double that for Gen 6, and you'd end up at like an 80-watt figure or something like that. And that's not true. And that's because, and we just kind of surveyed some data from the industry here, power efficiency trends are improving. So for, if we look at kind of using just one metric on random reads, KI ops per watt, you can see we've taken our power efficiency up from 10 to 15 watts Gen 3 to 20 to 25 watts Gen 5. And since we took, two factors of 2 performance improvement, it was good to see that the power didn't go up by a factor of 4 as well. So these power efficiency trends, and you can kind of look at what we've seen there and kind of draw a line and kind of, well, it probably looks like that. Somebody made an observation, that looks kind of like an improvement of about a factor of about 1.4 per generation. And someone said, I wonder if that's square root of 2, and I don't know. Maybe there's some fundamental mathematics that justify it, but for every doubling of performance, we are not getting a doubling of the power efficiency trends. So we're going to see the power of the SSD, at least to worst case workloads, increasing each generation. And it looks like if we, draw the same trend for Gen 7 or Gen 8 or Gen 9, or are we ever going to stop? Then this is going to continue unless there's some bigger breakthrough. I'm not going to describe that necessarily directly today. I think the power efficiency trends, there's a lot of conversations. It's a big term today. you're going to see me in my call to action. I think we need to start thinking about, are there ways we should be reporting power efficiency trends, monitoring power efficiency trends, et cetera. So informatively, and I'll call this out again in a little more detail in a second, EDSF said the E1S and E3 form factors are 25 watts. And so if I kind of draw a line of what we think we've seen in the industry of the Gen 5 drives being on the order of 20 to 25 watts in a data center situation, that's probably going to imply a 35 to 40 watt. Does that just break those 25 watt form factors? And we should just start thinking about taking them out of our design profile. So are there options to benefit from Gen 6 without moving to greater than 25 watts? Curious question. Have any of you guys been exposed to any of these conversations or concerns? Is this an industry thing, or is this just a me thing? Trent raised his hand. Thank you, Trent. John did. Yeah. So I think there are people that are questioning this, and I think this is a fairly safe way of forecasting. Just looking at energy power efficiency trends, that this is going to be something we're going to have to deal with. You know, literally, if I take the 140 K IOPS per watt, kind of throw some measly number like 4 or 5 million IOPS, it could even exceed 40. And what are we going to do about that? So we have options. The easy one, which I'm not advocating at all, just abandon these harder to cool form factors as we transition over to Gen 6. Well, we can keep the form factors, but just limit them to a 25 watt power profile or power state in NVMe. Tolerate higher operating temperatures, higher airflows with higher power states. I think I heard one presenter one time say, yeah, 25 watts is what we used to think about 3 years ago. We've moved on since then, or something on that order. So what can you potentially pull out of these things? And then this presentation is going to think about a bit of some more out-of-box thinking around some of this. And I think Trent offered a great introduction from his last presentation on this to help talk about this. So really what our goal is to try to see if we can offer some insights to how to rethink some of the power and thermal mitigations at both the host and the SSD. And these mitigations are aligned to NVMe, so I'm not asking for some new, let's break the standards view of the world here. So quickly, what are the standards? Within NVMe, there's some standards around powers and standards around thermals. And so a drive can report a table of possible active power states. PS0 is always the highest power state. And sometimes the question is, what is your PS0 that you want to declare for this drive? And then you can have a set of progressively lower power states. Direct quote out of the spec says, host may dynamically modify these power states, and Trent even gave a hint to some of that potentially as well, which is using the features command, optionally persistent. You could actually change the power states dynamically of a drive. And finally, just within this, we just got to remember that there is a PCI slot power limit that needs to be honored. And PCI slot power doesn't necessarily have to mean thermal power. It just means what's the regulators able of taking. On the thermal side, there is something called composite temperature. And so there can be many sensors on a storage device, and they get combined into one reported value that's typically used for management. And then there's something called host-controlled thermal management. And within host-controlled thermal management, ultimately you're setting two parameters. They have defaults leaving the factory, which a lot of people leave alone. OCP spec even recommended values for these things, but they're also settable by the host. And that's something called the TMT1 thermal management temperature 1, which is when you begin throttling, and TMT2 when you accept heavy throttling. And the spec also says you can have a vendor unique thermal action for the host controlled thermal management, or you can transition power states. And I'm going to make a recommendation of one way of mitigating some of the high power of Gen 6 by using a certain type of HCTM approach that I'm going to show you guys about. And then finally, there is a warning and critical thermal notifications, the warning composite temperature and the critical composite temperature. They are not the same as TMT1 and TMT2. So they can be the same. I think I've seen many cases where they are the same. But there's no reason why the warning bells need to align to the throttling points. That's a choice that the host can also configure or set as device defaults. And OCP offers some recommendation. Comments, questions? Oh, by the way, ask questions on the fly, guys. We got plenty of time. So if you have anything, just chime up. Font's a little small here, but I just grabbed a screenshot of the E3, and in there, in section 6 informative only, is thermal characteristics, and here comes the well-known E3S 25 watts and the 2T E3S 2T 40 watts, and as Trent mentioned, the E3L 2T 70 watt. These are informative only. Interestingly enough, I asked the same question, where did these numbers come from? And kind of get the same answer. As far as I can tell, they were inherited to some extent. I'm not exactly sure where some of these figures came from. It doesn't look like somebody did a study of NAND device physics and understood NAND reliability temperatures and picked thermal capabilities of these things to pick these numbers. It's, I'm not actually sure whether they were even set on touch temperatures either. If anybody has any history, I'd love to know, but there they are. And then finally, OCP does set a paradigm of thermal throttling only for failure conditions, and there's this famous graph, T-throttle 3, that says, well, our target is to run our host BMC managed fan speed to target 7 DC, but there may be a critically under-damped overshoot associated with that. So they're saying, well, there may be a point where in the process of getting to 7 DC and getting the fan stabilized, it'll go as high up to and past 7 DC, and they actually called out even what percentage of the design life may be above 77. But the paradigm from OCP is that the fans are typically for failure conditions only. They're not, the throttling is only intended for failure cases, and they don't want to see throttling in any other case. And there's maybe some justifiable reasons why, which we'll get into. Suresh, can you climb up? Yep.
Hi, everyone. Just by way of introduction, my name is Suresh Rajgopal. I work in the SSD organization very closely with Steve. So before we go into talking about some of the mitigation mechanisms that Steve was bringing up on how do you manage power excursions about 25 watts and maintain performance, I wanted to spend a little bit of time on how power is actually measured typically and what we do with it. So usually you collect current or voltage samples that are then averaged over a certain window, and these are done across, you take the median or the max over multiple windows for a certain duration, and then that's used to define the power measurement. So as you can see in that chart over on the left, which shows different averaging windows and the power levels, the value you measure for the power tends to vary significantly depending upon the window used. And there's a reason for that, because these averaging windows are used for a certain purpose. So anything, sub 100 microsecond is typically used to dictate regulator or decoupling capacitor considerations. What's called peak power is typically a 100 microsecond window, and that's used to drive things like power rail dropout, IR dropout, or brownout conditions, and that's what you typically want to track peak power. And you can see from that profile on the bottom left, you're looking for those excursions, and you want to make sure your power rail design and your regulator design is capable of handling that. But when you look at what's max average, that's the 1 second average, and this is typically what OCP calls out as a 1 second or greater max average. That is usually what we use to look at the thermal response of the drive, is how does it respond to temperature variation. And that's the part that we want to look at right now to see. And you can see that number is a lot lower than the 16 or 18 watts that we see up there. So the
key point to bring up here is Power is not power is not power. I almost call it regulator power, thermal power. So, yeah, so if your thermal guy would go design for this number around 17 watts, he would likely be overstating the thermal needs of that solution. They're probably closer to the 12. Or if the regulator guy hears 12 watts, he might under-design the regulators for the system by doing this. So these are very different terms, and it's always good when you're talking, are you talking thermal power, electrical power, because they are different. But the OCP spec does call out this 1.5x, and I think this turned out to be about 1.45 based on an actual sample here, but it's not uncommon, and there's probably some grounded mathematics associated with this, where based on the difference in the averaging windows, you get this figure. There is something concerning in the OCP spec that does talk about above 29 watts, this number needs to go to about a 1.7,
yeah,
something like that. And it's just like, well, at least in the data that we've seen now, it's sometimes questionable whether that's going to be doable or not. And is it grounded on the right mathematics? But in general, there's going to be peak for regulators. Max average is what's deemed as thermally relevant, and the OCP standard brings us out, and that's what we're using it.
Yeah, so like Steve was saying, I think the terminology is quite important. It's, and depending on who you're talking to, if you're talking to an ASIC designer, an NAND designer, a system designer, when they use the word peak, you want to make sure, the connotation is clear. What are you averaging over? What are the windows? So now the question is, what is, the gradient or the range at which the temperature can vary when you're looking at the thermal response of the drive? So we looked at a couple of scenarios here. This is, if you look at the chart here, this is tracking the composite temperature that Steve talked about, which is really the aggregate of all the sensors on the drive responded to by the drive that the host monitors, varying over time for two form factors running two workloads. One is the E1S 15 millimeter, it's a smaller form factor, the other being the E3S 2T, a larger form factor. And both these drives assume no throttling, same power, similar airflow and temperature conditions, so the ambient temperature coming in is the same on both. What's interesting to note is to really look at the gradient, which is the slope at which the temperature changes over time. With the E1S, you can see a much higher gradient relative to the E3S just because of the thermal mass differences between the two form factors. And that's really kind of the main takeaway, is that depending on the form factor and the airflow capabilities, this temperature gradient on the, can vary anywhere from, 0.25 on the E3S 2T versus, say, a half to a 3/4 of a degree per second, going from idle to a full workload. So this is kind of, when we talk about thermal response to the drive or the temperature, this is the variation that we're looking to track. Now, how does this compare between a synthetic workload versus a real workload? One of the questions that Steve had in the previous talk was, when you talk about a 40-watt max power, are you assuming that every single drive on that entire 2U is operating at that max workload? And so we did a couple of profiles here. The one in the bottom first, which is your standard, what an SSD typically specs, steady state, sequential write workload. You can see this has a very tight range. It's within 2 watts. The one on the top is more a real workload. This is an MLPerf storage workload of medical image segmentation. And you can see this workload is extremely bursty. There are periods where the power goes down, and then there are periods where it peaks up. So these real-world workloads are very bursty, and there's durations where you need the higher power draw, and there's also durations where you don't need that higher power draw. And that's really the takeaway here.
What's the measurement for each time?
Seconds. It's the same, the 1 second average.
Max average.
Yeah, the max average in OCP.
Is that the same drive in both of those?
It is, yes. So now as we lead into the power and thermal throttling, we thought it would be useful to walk through sort of a conceptual view inside the SSD, one example of how it would go about performing a power throttling or a thermal throttling. If you go look at the top part, you've got your host command coming in, goes through a decode, and then eventually it gets translated into a NAND operation that then feeds in the back end, and there's a certain amount of power you're going to consume for that NAND operation, whether you're going to read or write from the media. In addition to that host traffic, you've also got the SSD generating additional traffic back to the NAND for garbage collection, any media operations, et cetera. And that also funnels into the top. So now you've got power coming in. There's a certain amount of power that you need to keep the SSD operating. On the left-hand side, you've got another task going on. This is the monitoring of the SSD composite temperature, and that determines what temperature profile you're required to operate under. And in the event that you exceed that, then there's sort of a derating factor that tends to get fed in. So what happens is you've got a certain power state that has been set, depending on whether you're operating at a certain PS0, PS1, whatever it might be, that gets set, and then the derating factor will tell you what is the maximum power that the drive is actually given, and then that is then compared with the power that the drive needs to deliver the performance. So in the event that that power allowed is actually less than the power that you need, that means you got more power than you need to actually perform, then the operations continue, you don't have an issue. But in the event that you don't have that power, that's when action needs to be taken to throttle in some form or the other, and that's accomplished in some form. Effectively, you're stalling. And the stalling typically will induce latencies. You could perform the stalling in different ways, but that's the net effect, is that now you're throttling to stay under either a thermal level or a power level, and so you're inducing these latencies. And Trent mentioned this briefly in his previous presentation, that there is an impact to this latency. And so this is a typical survival plot, essentially showing you over time, the different nines that you see for your quality of service, and it plots two specific power states, a PS0 and a much lower power state. And you can see that the lower power state obviously is a state where you are throttling the drive, so you're inducing those latencies. And when that happens, you're going to have those tails increase. And so the latency will increase with either a power throttling or a thermal throttling, depending on what you're intending to accomplish. And so the whole goal of this exercise is that if you want to make sure that the drive is able to deliver the performance when it needs that burst power, you want to minimize the time that it stays in this throttle state. So you want to minimize this residency in throttling. And that's the exercise that Steve's going to touch on now.
So I think the point we were trying to make is, it doesn't have to be this way, but this is common. Throttling is throttling. So you have throttling for power states, you have throttling for thermals. They can go into the exact same mechanism. And this has been my experience, as they go to the exact same mechanism. So I wanted to walk through a couple of potential examples of what we could possibly do here. So in this particular case, I'm going to pick a form factor that cannot tolerate the sustained workload, and something is going to have to happen here. So one option would be just to set the power state to 25 watts, and then you would just always be in this residency of the latency when you're running the sustained workloads. But do you have to do that? If you have thermal margin, why are you throttling when you have thermal margin? And if you just set a power state, you are going to throttle whether you have the thermal margin or not. So let's play a game where we don't do that. So we start at this PS0, and we're not throttling, and then the temperature starts rising. At some point in time, it's going to exceed the power targets, either for the platform or for the SSD or both, in which case you could transition to a lower power state. And in the lower power state, in theory, the temperature would decrease. And at some point in time, now you have thermal margin again, you could turn this back on, temperature would rise. down, up, down. And so effectively, you end up with, in the cases where you have no throttling residency, you have a latency curve that looks like this, and when you have throttling, you have this other latency curve. And this is where we talk about this residency of throttling here. And in this particular case, and I will admit this is somewhat of a cartoon example, somewhat arbitrary, but the curves did match the curves that we showed on temperature over time. This was about a 60% throttling residency. So running that sustained workload, you could either have 100% residency, or you could possibly have a 60% residency within this workload. And there is a bit of, sarcastically, sometimes I call the throttling whiplash that occurs within this, and that's associated with that. Comments, questions? Make sense? Another option here. Actually, I'm going to back up for just a second here. On this picture here, you'll see that I actually proposed using TMT1 and TMT2 here to generate this derating curve. So based on the composite temperature, we generate some progressive derating within here, and that becomes a multiplier. Well, what happens if I run this progressive workload here? So in this particular example, I set TMT1 at about 65 centigrade here. And as soon as the temperature starts rising above 65, you start slowly adding a small amount of derating. And then as the temperature continues to rise, you continue to add more derating. And then at some point in time, the thing just stabilizes out. And so what will happen is rather than having the sawtooth, you end up kind of landing at the average of what the sawtooth would have been. And rather than having a 60% residency on, off, it just will kind of land at that 60% residency point and just stay there and not have the whiplash associated with the latency distribution. So rather than going back and forth on the latency diagram, rather than having your 6 nines bounce between the green line and the blue line, it'll just kind of land on that purple line and stay there. And that would be to a steady state workload or a sustainable workload. So the idea is, one way or another, if we have thermal margin, why not allow the bursting capability? Only start derating and inducing the additional latencies if you're starting to approach upon your thermal margin, as opposed to just setting a power state forever to go do that. And then you would just always be in the residency of the blue line. Make sense? So what we're saying is we have options here. So if you want to just align your power states to the form factor recommendations, certainly doable. Hosted manufacturers set default power states. They're unmodified over the device life. I think there was a lot of discussion, which is you can't have a PS0 greater than 25 watts on E3S 1T or E1 form factor drives. They need to be lower. And the answer is, well, maybe why not? Allow some power states above what would be thermally sustainable. And it doesn't necessarily have to be the default power state, but you can at least have this. This solution gives you, I think, greater overall throttling residency. You're spending more time stalling transactions because of that. You'll even throttle when it's not thermally necessary. You may have 30 degrees of temperature margin, but you're above 25 watts, so I'm going to throttle it. And at this point in time, I think arguably the way from the power efficiency trends looks like a Gen6x4 full burst performance is not available. I still think it has a lot of values to be in Gen 6. There's just more upside to be realized. There are a couple different options beyond this. One would be to allow the host to manage dynamic power states. So the host can periodically poll the C temp, and which is why we were kind of looking at that curve going, well, how fast would you have to poll it? And we think it's sub 1 degree per second. So if you're worried about a 7-second overshoot, poll every 7 seconds, 10 seconds, something like that. Or you could poll potentially faster, and the host would decide some polling interval. And if the host does see getting close to its thermal limits, then it can start reducing power states, and it can just set the command for the power state. The latency profile does shift back and forth when you do this, but it does enable some extended Gen 6x4 burst capability within the system. This is, I think, probably best managed through BMCs, although there's no reason why the host side couldn't do this as well. But the assumption might be that the host is just periodically polling for various reasons on the C temp, and at least the OCP spec implies it's doing that already for fan temp. It could also not only adjust fans, but adjust NVMe power states as well. The other option would be to let the drive handle all this through the host controlled thermal management. The host would just set its TMT1 and TMT2 values, and then the drive would just internally poll and adjust the throttling progressively. There's no concept of kind of progressive NVMe power states, so you would take these quantized jumps as opposed to kind of being more potentially linear within HCTM. You will reduce your throttling redundancy just like the host doing it. But it'll give you a consistent latency profile using HCTM. And this is something I wanted to kind of everybody to kind of start thinking about and noodling. We can clearly modify or poll fast enough. We can adjust much more progressively than just jumping NVMe power states. Either of these options are available, and ultimately leads to our call to action on this, which is beyond just respecting the slot power. I think supporting NVMe power state 0 above the quote thermal TDP of the profile makes sense. Why not throw a 30, 35, and 40 watt power state on a form factor that claims 25? That doesn't necessarily have to be the default when it wakes up out of the box, but at least gives a host an option to do this. And the host guys spend some time thinking about this. We've talked to a couple folks that are already using their BMC to manage this. And if you're not, it might be good to start considering this. I think the HCTM is probably the newer bit of this and is probably worth some future conversation between the host and device vendors on whether that makes sense or not. There is the storage management initiative in SNIA. There's OCP hardware management, and then Linux Foundation Open BMC, I think, are all places where this could also be discussed further. And then finally, it'd be nice to get some power efficiency metrics other than worst case workloads. Someone gave the analogy one time. We measure miles per gallon with the throttle slammed against the, slammed on the car. Those are the only power efficiency metrics we have, but that's not how these things are really driven. So in the client world, there's applications like MobileMark that are real workloads, and from real workloads, we can go do this. Another example I can always give is the Environmental Protection Agency requires automobiles to have two workloads, a city and a highway workload, and those are standardized workloads with standardized methods and then standardized ways of measuring the result, and then they post those two figures on the sticker when you're buying a new car and you're all familiar with it. So I think finding ways of maybe picking a couple bookmarked workloads that might kind of give us the equivalent of a city and a highway MPG will allow us to take a look at this thing. Plus it will factor in some reality, like in the EPA city, it includes spending time at a stoplight. So what is your power efficiency idle? Nobody seems to spend much time thinking about that outside of the EU Lot 9 request right now. But I think there's definitely an opportunity to start looking at some of these power efficiencies, which is, with any luck, will be some of the discussions I'll bring in next year. Yes, sir?
In the host activities there, you've got participate in SNIA, storage management initiative, OCP hardware, Linux Foundation, Open BMC. Have you looked at the SNIA green quick?
I have not. Thank you for the pointer. So, any comments on that?
They've been doing some device level work there recently that this might dovetail with.
Good, thank you for that.
Thank you. I was going to bring that up. They are actually developing a Calypso-based standard workload, which actually tests the device under a variety of read-heavy, write-heavy, mixed platforms, and they will spit out the IOPS per watt, bandwidth per watt, a bunch of fun stuff for each of those states, and they have stabilized, or they have defined ways to get to steady states for each of those conditions. So it's fairly interesting. It's on Wednesdays for 2 hours. Also for PCIe, there are a couple of different ways to set power these days. We should all move to their terminology, which is max sustained and peak, to cover the larger window where you care about thermal stuff. And
How does that compare to the OCP figures? I think aren't they aligned or the same, or?
I didn't actually see the max sustained in your talk. I don't remember what's in OCP. I'll have to go back.
Yeah, it's not, it's OCP called max average and some max sustain.
Yeah, it would be good to move to the normative names. The other thing
Okay.
that, given the latest PCIe, there are multiple ways to set power budgets now, in addition to setting slot power. So it'll be interesting to see how we move. Some of them are actually better for multiple function devices.
Yeah, I think it's, some work needs to be required to get that aligned to NVMe and OCP, and agreed. And I did, make it clear that we definitely need to honor the slot power, so if the slot's reporting 25, you're not accepting a 40-watt power state, and,
NVMe requires you to use the slot power as an additional maximum, and you have to run at the lowest. So you actually have to support the slot power commands if you want to go above 25.
Just out of curiosity, is that slot power a peak or a sustained?
That is the sustain.
Same.
Max sustain.
And everyone is trusting some multiplier to get to what the regulators actually need to support above that for the peaks that aren't covered by filter capacitors. And yeah, so if anything, just power is not power is not power. And when you throw around a number like 25 watts, are you talking thermal power, regulator peaks, or something else? Any other comments, guys? If not,
One minor comment. You were showing the sawtooth curve, but the response time for a lower performance or a additional latency, the temperature gradient that comes down, is that going to be uniform like you were saying, or is it going to be varied? I feel it will vary. If you go back to one more slide, move forward.
Host view shared one.
Forward? Yes.
This one.
So here you're showing that I go to a low power state and then my temperature comes down quickly, right, or at least in the time window. You see that, or is there a cumulative effect of taking longer and longer and longer to bring down the temperature?
this is admittedly a cartoon. This is not based on, actually I have a little spreadsheet thermal model that generated this picture here. So it's not a precise ideal thing. Go ahead.
Temperature does not have hysteresis. Temperature does not remember being hot previously. So it'll be the same slope every time you go to a reduced power state.
You could see that even with that workload where we track the two different workloads. As the workload transition went idle and then it ramped up, you will see that. Now obviously the workload is different. You're going to see a different max level that it reaches to right here. So one, say, a read workload versus a write workload, you'll see that. But other than that, you will still see a drop in the temperature.
That is it given the constant airflow?
Yes. This is, yeah. But this is assuming you're not changing.
You see, right, in a system, the airflow would also increase in response to higher temperature.
Correct.
If I read from device, and then I reduce the airflow as see the temperature go down, there is one.
Then the profile would change, yes. So the assumption here, of course, is that it's constant, but you're right. In a real system, besides reducing the power state, you would possibly also resort to an action of increasing the airflow, and which would then change the gradient at that point.
That's a good point. There's a feedback loop with the airflow going on as well, and or at least the assumption out of OCP in this as well. I'd love to keep talking to you guys after hours on this, so
I'll throw in one more comment.
go for it, John.
In your chart of AI ops over watts, over gens, one of the things you didn't account for is what we NAND makers keep doing to change our internal structures. And there's actually a whole nother bit of invisible hand that's going on as we increase our internal interface speeds. Because the more speeds you have, the less NAND devices you have to have turned on.
Yeah, and this is trying to just capture that at the aggregate level. I mean, we were asking the question, where is this power efficiency trend coming from? It's like, well, okay, advanced litho in the controllers, the old CV squared F, advanced lithography typically reduces power, but then we typically take advantage of that advanced litho and up the clock speeds to try to get more work done. So there's a push-pull going on there. There's also, like you said, a lot of work that the NAND guys are doing to, I've heard it expressed sometimes in picojoules per bit or something like that, is, that those trends tend to improve with time as well. So we were frankly proud of ourselves to not just say, well, let's just look at Gen 4 and draw a straight line, or let's just look at Gen 5 and draw a straight line. We said, no, we expect there to be an ongoing power efficiency improvement over time, and it seems, at least over 3 generations, to be somewhat stable. But it is not greater than 2. So that means every generation is going to have a higher power potentially than the prior generation. We don't get to double speed and end up...
It is fair to say that PCI SIG architects swear each generation is getting more power efficient at the transceiver level, as well as our NAND engineers who are doing the Gen6 specs swear that each bit of transport at that level is getting more efficient per generation.
But maybe not 2x. Is the
Yeah, there's a lot.
it definitely there.
A lot of moving wheels in this.
There's been a tremendous amount of work to achieve the 1.4 that you're seeing here, and this will obviously continue. And again, these are industry trends. One guy may do something better or worse than some other vendor might do on this, but this seems to be the overall trend that we were able to observe. All right. With that, thank you guys. Happy to interact with you over the course of comments if you guys want to talk privately on some of this stuff. So thank you.